So it's a power series expansion about a point x equals a. So that's where you're centered at. Like we just talked about, the more terms we involve in our series or our polynomial, the more accurate the approximation we'll get. And then it says in some cases, the Taylor series will converge over the interval of a negative infinity to infinity. So the day we did the interval of convergence, we got one or two of them that did that, where we said the interval of convergence was everywhere. That means it's going to produce an exact clone of that graph. All right, and that's what that's saying here. All right, and then it says, by understanding the behavior at a single point, so we're going to do everything at a single x value, you will sometimes be able to construct the entire function. So if we go down here, wrap your head around that, but that is the formula for a Taylor series / a Taylor polynomial. Okay, and what you're going to see here, follow the little pattern. Notice how this is our first derivative. You have a first power, first factorial. Second derivative, second power, second factorial. Third derivative, third power, third factorial, so on and so forth. This is zero derivatives here because this is your functional value. I didn't write it, but this is really x minus a to the 0 power. So it's the 0 power, a zero derivative because it's your functional value, and then it's a 0 factorial. All right. And we all know that 0 factorial, and the calculator never lies with us. So if I do a 0 factorial, have I already showed you this? Have we already talked about this? All right. All right, if we had, I feel like I did at one point. Isn't 0 factorial obviously 1? All right. So very obviously, 0 factorial is going to be a 1. Okay, so that's fun. If we have some time, I have a little proof here to show you. I'd rather not. If you want to do it some other time, I'd be happy to. It's in my notes right now that I always show everybody, but I'd rather save a little bit of time. So for right now, just wrap your head around this, that miraculously 0 factorial has to be a 1. Okay, so that's our formula. So whenever we ask for a Taylor series or a Taylor polynomial, this is how we're going to be hammering this thing out. So this corresponds to the number of derivatives we take in. This should have the same exact power with the same exact factorial. Okay, so go to the next page, and we're going to go through one of these, and then you can kind of see what we're finding when we do this. All right, so leave a little bit of space. Let me draw a line right here. So leave a little space to do some work up in here. And then right underneath this, I'm just going to write out what we just said on the front page in terms of what a Taylor series looks like. So it's an infinite polynomial. We really could start anywhere. I'm going to start at 0. I'm going to change these to n's as well. I like n's better anyway. And then it's going to look like this. All right, so what we need is basically our functional value at a, and then x minus a to the 0 power over your 0 factorial. And then I want the first derivative, x minus a to the first power over 1 factorial. And then we just follow this pattern. Second derivative value, x minus a to the second power, 2 factorial. And then we just continue that. When we read this, so this is a huge distinction to make. When I ask you to find a Taylor series, the series is ultimately, our final answer is the whole sigma with the infinity and then whatever this general term ends up being. That's what we are concerned about if it says find the Taylor series. So the way we need to do this is we need to take your function of 1 over x, and we need to find our functional value at a equals 2. So pretty simple there. You just get 1 over 2. That's going to be our functional value. So that, when we go to write our formula, that's going to go right here because that's our functional value at that time. But what we now need is our first derivative value at 2. We need our second derivative value at 2 on down the line. So understand this is, just for the sake of a derivative, it's also x to the negative 1. So my first derivative would be a negative x to the negative 2. Which is just a negative 1 over x squared. So that if we now find f primed of 2, you would get a negative 1 over 2 squared. So that's a negative 1/4. So when we start filling all of this in, that's this value right here. We're going to slot that in for f primed of a. We need a second derivative. How far did I go here? We definitely need the second derivative. I think I went to the third. So let's do our second derivative. Do it with this version. So that's now positive 2x to the negative 3. So the second derivative value at 2 should be 2 over x cubed. So 2 cubed, which is what? 2/8. So that is also going to give you a 1/4, but positive. And then on mine, just so we can kind of see the pattern, I want you to do one more derivative. So find the third derivative. So that should be a negative 6x to the negative 4. Throw your 2 in. So we'll get a negative 6 over 2 to the positive 4th in our denominator. Yes, that was my dog. Negative 6 over 2 to the 4th is a negative 6 over 16. So that's going to, what does that reduce down to? Negative 3/8. So that's going to be a negative 3 over 8. All right. So once we have all of those, here's how we're going to now set this up. What we are going to create over here by just using this formula and then these derivatives is basically a reproduction of 1 over x. So on the left-hand side, put 1 over x. And we're going to start to fill in the Taylor series that will approximate or give us this function. So our functional value we found to be a 1/2. So you're going to put 1/2. And then for the first few, I am going to write this, even though it's obviously unnecessary, but just so we understand this pattern. But really, that's just going to be your functional value will be your first term. Then you're going to do plus, and then we want the first derivative value, which we found to be a negative 1/4. And then we want x minus 2 to the power of 1 over a 1 factorial. Then we want our second derivative value, which we found to be a positive 1/4, x minus 2 squared over 2 factorial. And the last one that we did is our third derivative. We found that to be a negative 3/8, x minus 2 cubed over 3 factorial. The reason we're doing these, we kind of want to see this pattern a little bit to figure out what the series is going to ultimately be. So in the next thing, we need to try and come up with this. And we probably want to simplify this a little bit first, but this is ultimately what we are after. So in the next one, let's clean these up now. So now let's simplify this. So this is going to be a 1/2. This would end up being a minus x minus 2 over 4. The next one turns into a plus. I would have 1/4 divided by 2 factorial. 2 factorial is just 2 times 1. So 1/4 divided by 2 should be an 8. So I have x minus 2 squared over 8. And then the last one switches to a minus sign because it was a negative 3/8. Let me do this over here just because I'm running out of room. We need to do 3/8. So negative 3/8. And I'm going to divide that by 3 factorial. So that's really the same as multiplying by 3 factorial, which is 3 times 2 times 1. So that's really a 6. So when I do 3/8 divided by 6, that should give me what? Negative 3 over 48, which reduces down to be a negative 1/16. So I just did, just so we understand what I was doing, I did this negative 3/8 divided by this 3 factorial. And when we did that, we get a negative 1/16. So I will get minus x minus 2 cubed over a 16. And then now, let's see who's really good. Write that general term. Although, hold on, let's start this at 0. All right, it's not way too long here. We see it's alternating signs, correct? So as I've kind of mentioned, we're doing these and we're trying to create them. If we're doing the antiderivative, if we're coming up with them on our own, whatever, let's just treat that as kind of its own separate little term. It gives us one less thing to worry about. So I'm starting mine at n equals 0. So I would want my -1 just to get raised to the power of n. Then if I look at this first term, while we don't have it written in, I could have had this as an x minus 2 to the 0. So notice how we have an x minus 2 to the 0, and then to the 1, and then to the second, and then to the third. So we obviously need to have an x minus a 2 in here because they all have that. And then doesn't the power just correspond to whatever n that we are plugging in? So this should just be x minus 2 to the power of n. And then in our denominator, when I plug in a 0, I better get a 2. When I plug in the n value of 1, I better get a 4. When n is 2, I better get 8. And when it's a 3, I better, 0, 1, 2, yeah. All right, so when we do that, that should give us, anybody think they know this? Safyan? Good. 2 to the n plus a 1. If I let n be a 0, I get the 1 that I'm supposed to get, 2 to the 1. If I let n be a 1, I get 2 squared, so that's the 4. If I let n be a 2, I get cubed. That's going to give me that 8. This is our series. All right. Until we have the series, all right, it's an approximation. So like up here, what we could actually probably would do as we move forward, without having this series, the only way we can ever use an equal sign is if we come up with every single term that approximates this function. And the only way we can do that is by writing the general term from 0 to infinity. That then gives us every single term in that function. So here's what this now means. So let me kind of show you what this is setting up. So let me turn off the polynomial term. So if I turn that off, here's what the 1 over x graph looks like. Now, remember, we're centered at 2. We got all this information at the x value of 2. So these are all of our functional values at 2, derivative value, second derivative, third derivative value at 2. So if I graph 1 over x, here's what that graph looks like. Really focus in on what's happening at 2, because that's where we're centered at. So if I now turn on the polynomial that we just created, so these are the exact same things that you have on your paper, I promise. Start looking at 2 and notice how this graph starts to replicate 1 over x at 2. So see how around 2, you can't really differentiate at all around the 2. The further away we get from 2, they start to kind of go off on their own direction. If we wanted this blue graph, the polynomial, to replicate the red graph for a longer period of time, we would just want a 4th derivative, a 5th derivative, a 6th derivative, and each time we do that, it's going to replicate even more of the red graph, and they all start at the x value of 2. So what the previous page was saying is, all we really did is took a whole bunch of derivatives, use that formula, and we can start to actually replicate whatever that graph was, whatever that function was with our polynomial. Okay? All right. Are we good to that? Follow all that? Okay. That's kind of what this is saying. It says, graph the polynomial terms. I did that for you. Does the series converge to 1 over x? It did, because that's the overlap. And it was overlapping at the x value of 2. That's where things started to string together. All right. So what I just showed you on the calculator is what these 3 bullets are trying to show you. All right. So now number 2. Notice how this doesn't ask for a Taylor series. It's asking for a Taylor polynomial. So we don't need to find the general term. And when it says of order 3, what that means is we need to get to the third derivative with the third power divided by the third factorial. So that's what, if we have a third degree polynomial, it's that power of 3 in the third factorial. So with this one, we know our function is sine of x. So these derivatives should be short and sweet. So we need to hammer out 3 derivatives. So do that since we need a third degree polynomial. And then we want to evaluate all of those. In order to use our formula, we need to evaluate them at pi over 4. So for all of these, you get some variation of root 2 over 2, either positive or negative. So this should be a nice one to get through quickly. Okay, so hopefully we're all to here. So now here's how we have to kind of differentiate right off the bat. Up here, since I was finding the series, it really didn't matter how many terms we used. I used 4 because I think after 4 you start to see the pattern pretty well. But we can use an equal sign here because we're writing ultimately the series, that this actually does represent this. When we're using a polynomial, we don't want to say, so we don't want to now say sine of x is equal to this. You could conceivably, if you want, write the sine of x is approximately this. But if we're only going to write the first handful of terms, there's no equivalency at all. The way this really gets written most of the time is we're going to write this as, notice how we want a polynomial of order 3. We write this as a p with a subscript of 3. So that's just saying this is a polynomial of order 3. Then we can use an equal sign because that's what we're truly finding is the polynomial. And then now we need to throw into that wild formula. So the first part of the formula is your function value. So that's just root 2 over 2. You can if you want. You don't have to, but just so we understand the pattern, x minus pi over 4, and then we would divide by 0 factorial. So it's all the 0 stuff. 0 derivative, 0 power, 0 factorial. Then you would add, then we want our first derivative value, so root 2 over 2. We want the x minus pi over 4 to the power of 1, and then we want that all over 1 factorial. Then we want all the second power, second degree stuff, so second derivative. The x minus pi over 4 has a second power over a second factorial. And then last one, again, since we want order 3, that means we want all the third derivative power factorial information. So it's another negative root 2 over 2. The x minus a pi over 4 to the power of 3 factorial, and that is your answer. You could simplify it if you want. So if this is a free response question, you are absolutely leaving it like this. If it's a multiple choice question, then you probably need to go through, simplify it, and figure out which one it matches up to of the selections. But this is our Taylor polynomial of order 3. All right, and then that's it. If I want to approximate the sine of, let's say, pi over 2, same exact thing. I could find the polynomial value at pi over 2, and this will give us a rough approximation for what that value would be. All right, we're not doing that though, because we're moving on. In fact, number 3, we're not even going to do. Even, I think, in class, I skipped that one. Today, we're definitely going to skip it so that we can actually finish this. So, old free response question, 100% guaranteed. Whichever version of the AP test you were taking, you are going to get a question on this chapter, and it is almost always a Taylor series or polynomial, or what we do tomorrow, which is really similar. So this is an old question, word for word. So number 3 says let p of x, so that's a polynomial, and then they give you this as the polynomial, be a 4th degree, and that's because they get to the 4th power. Taylor polynomial for some unknown function. So now we just don't know the function. Assume f has derivatives of all orders for all real numbers. If you understand what we are doing, f of 4 is very, very easy. F triple prime to 4 is also pretty easy, but you might not think it's easy just yet. So find f of 4. That, if we're understanding, couldn't get any easier. And if I ask you what it is, we could all make this with two hands, right? They fit on two hands. All right, because isn't this your functional value right there? That first term should be your functional value. So f of 4 is 7. We all got a free point right there. We're well on our way. Then we need our third derivative value. Well, we know what the formula is. When we use the third derivative, don't we usually take the third derivative? In this case, it would be at 4. Notice how we're centered at 4 all the time. So the third derivative at 4. And then we would have had x minus 4 to the third power, all divided by a 3 factorial. So shouldn't what we have right here, shouldn't that correspond to this term right here? So that's our third degree, and this is where we would have gotten that from. Well, notice how they both have this x minus 4 cubed, so we don't really need to worry about that because they both have these. So doesn't this fraction right here, doesn't the third derivative value divided by 3 factorial have to reduce to give us this little negative 2 right here? So we can basically just say that the third derivative value of 4 divided by 3 factorial had to have equaled this little reduced version, which ended up being a negative 2. Really, really common question. And then quickly, 3 factorial is a 6, right? 3, 2, 1. Multiply that over. This had to have a value of a negative 12. Okay. So those, moving forward, you will now think that one is also easy when you see that in the future. All right, letter B. It says, write a second degree Taylor polynomial for f prime. So keep in mind, p of x is an approximation for the original function. So in many ways, while we don't want to say f of x is equal to this because it's an approximation, this really is your function. So if I simply want f primed of x, then if I go ahead and write this p of x as 7 minus 3 times x minus 4, and x minus 4 squared minus 2x minus 4 cubed, 6. So I just recopy that. This is an approximation for f of x. So you can put this, I suppose, because it's an approximation. Well, if I want to approximate the derivative, all the derivative would be, if I want to approximate that, would just be the derivative of what we just are given to work with. So now we just basically take the derivative of that polynomial function. The derivative of 7 will go away. It's a 0. Drop down the negative 3. And then wouldn't the derivative of x minus 4 just be a 1? So we really, the 7 goes away. The derivative of this is a negative 3. Plus, got to do a little chain rule here. So remember how we do the chain rule. So the one that I'm highlighting, you're going to multiply by 2. So 2 times 5 will give you a 10. Leave the inside alone. The new power is a 1. And then the derivative of the inside is just a 1. So you don't necessarily have to show that, but just to make sure we understand that chain rule. Keep in mind what we're looking for. We want to use a second degree polynomial, correct? We're currently at the first degree. So the next one should be our one that we need to stop at. So now we're going to do the same thing with this one. So we now need to take the derivative of this. Power chain rule again. So 3 times a negative 2 would be a negative 6. X minus 4 squared, and then the derivative of the inside would be a 1. So we now have our derivative. We now have it to the second degree. So now we go ahead and say that we want to figure out what is that polynomial's value at 4.3. So wherever you have an x now, plug in a 0.3 or 4.3. And then whatever that gives us is our answer, sort of. You want to write it correctly. But it'd be calculator at this. Yeah, that's a good question. I don't remember if this is calculator or not. Could go either way, really. But when you throw that in, that should give you negative 0.54. And then just be really, really careful, because this is something you don't want to give away points on. Because again, this is going to be a free response question. What we are ultimately looking for is an approximation for this guy. So the way you're going to present your final answer is you are going to say that f primed of 4.3, don't leave it like this as a polynomial. It's an approximation, so you must use that approximation symbol. And then you say that is the negative 0.54. Okay. So letter B, we took the derivative. If you then now go down to letter C, we want to find a fourth degree Taylor polynomial. You're going to call it g of x, and all that is, you're going to integrate this function. So again, this up here is basically the approximation for our function. This is telling us we want to integrate that now. So to set up g of x is the integration from 4 to x of f of t. So know how that's going to get set up. You're going to do an integral from 4 to x. And then we are, for the most part, copying that function at the top. So we start with 7. And then we would have had minus 3. Be careful here. We don't want to put this as x minus a 4, even though that's what the original problem says. We want it to be a function of t. So they're telling you to change the variable that we are working with to a t. So this now needs to get changed to t minus a 4. And then plus 5, just continue this on. The t minus 4 squared minus the 2, and then t minus 4 cubed. Notice there's another term in the original problem, but we want to stop here. We want to stop putting those, because if I want a fourth degree polynomial, and I'm going to be doing the antiderivative, if I do the antiderivative of the cubed term, won't that then take us to the fourth power? So that's why we know we need to stop at that point. Oh man, I didn't leave enough room, did I? All right, so go ahead and do the antiderivative of those. Shoot, that's not good. I'm just going to cancel across this out. What I was thinking. So then g of x should be, now to start doing your antiderivatives. So 3 t minus 4 squared divided by 2. Plus our 5 we ignore, and then you do a t minus 4 cubed divided by 3. Minus 2t minus 4 to the 4th divided by 4. Notice how we have our fourth degree. That's ultimately what we wanted. So that's why we stopped with that term. We're now going to evaluate it from 4 to x. Plug in your upper limit. So all the upper limit getting plugged in puts it back in terms of x. So all the t's just become x's. I'm going to reduce this last one also. As we do this, the 2 and the 4 will reduce down. Minus, throw in your lower limit. The lower limit's actually nice. 7 times 4 will give you 28. But then any other one, when you throw in the 4, notice how those will all zero out. So the only thing you're going to get is a 28. Now, they're really, really clever. And this is really, really clever. Because this is sort of your answer, but if you wanted the full credit as your final answer, because we've done the antiderivative, it's in terms of x, this is what g of x is. Shouldn't a Taylor polynomial, shouldn't we, if I look at this one here, x minus 4 squared, x minus 4 cubed, x minus 4 to the 4th, shouldn't this guy right here, if we're going to be centered at 4, shouldn't this be an x minus a 4 to the first power? So here's where they get really clever. This is all one term now, right? Minus a 28. So couldn't we rearrange these guys so that we have the 7x minus the 28 next to each other? And then I'm going to use old English tricks and put a little parentheses, quotations there, just saying I'm going to recopy everything else down. If those are rearranged, can't I then factor out the 7 and end up with an x minus a 4 to the power of 1 like we are supposed to? Then everything looks like it should. Then we get full points. this is little stuff that if you catch on that day is really, really good. I wouldn't freak out about it if you think there's no way you would have ever seen that. 98% of the people don't see it, so that's okay. This would be our final answer. All right. All right. And then the last one. It says, can f of 3 be determined from the given information? So D. The answer is no. We can't find f of 3. What that's really asking for is I can find f of 4, right? We know what f of 4 is. You already did that in part A. I could find the third derivative at 4 like we did in part A. I could find the second derivative at 4 in part A. We can do a lot of that. We can't find the functional value at 3. We could approximate it, but we can't find the actual functional value because we are centered at x equals 4. Those are the values that we can come up with exactly. Everything else is going to be an approximation. All right, so we could approximate it like we did earlier, but it wouldn't be the exact value. All right. We skipped just enough to make sure we finish without having to race home there. All right, so with that, those are those notes, again, for tomorrow. So I feel bad having everybody who comes to school tomorrow have to sit at their desk with their computer and earphones in, but you're going to watch this next set of notes on Canvas. Those are posted. And then that's pretty much the end of our notes. That's the last section of notes, anything new that we really do this year. So as we come back then next week, we'll kind of review this material a little bit. And then probably Wednesday, Thursday, Friday, we'll start to focus a little bit on some of the AP test. And after that is the AP test and this test. And then our final. We got a lot of tests coming up here in the next 2 weeks. All right. So hopefully that makes sense. If you have any questions on the video, just reach out to me over the weekend or just pop in early on second period morning. And obviously I'd be happy to kind of walk you through that and help with any of those questions. All right. All right. Then have a good day. We will see you guys. Have a good weekend, actually, since I won't see you tomorrow, and we'll see you on Monday. All right. Bye. Yes, ma'am.